Hey there, welcome to my YouTube channel, Maths and Science Top Dogs. So if you haven't subscribed, please hit that subscribe button. Okay, so today we're going to take a look at the rank and the linear independence of a system of vectors. Okay, so check this. It's not a system of equations. We're checking the system of vectors where you have a multiple vectors and you want to check whether they're linear dependent or linear independent. So first, let's just define a single vector that we have. A definition of a vector, remember we're just reminding ourselves about this. A definition of a vector is going to be a physical quantity that has both magnitude and direction. So here I'm just going to give you a simple vector. That's given by is 3 and 2. This is the vector components. So you can actually express these vectors in terms of a linear combination of the standard unit vectors. Remember that in xy plane you have this is going to be x, this is a y plane. You have a 2 unit vectors here. You have 1 unit vector that has a magnitude of 1 at this point, which is going to be 1 and 0, and you have another one here which is going to be 0 and 1, and we call this one the I hat is going to be this vector, unit vector 1 and 0, and the j hat is going to be this one here, 0 and 1. So you can express any vector in terms of the linear combination of those ones. So here we can say if this vector is equal to, since this component is an x component, so it's going to be 3. You multiply it by 1 and 0, and you add it by this, which is 2, and you multiply by 0 and 1. This is a y component, this is an x component. So vector v can be in 3 I hat plus 2 j hat. So this is another way of expressing vectors. Okay, so now let's go to the linear independent. Here actually let's ourselves about what we learned in previously. Okay, so now let's go to the linear dependent and the linear independent. Let me shift this. Linear dependent and linear independent. So first, suppose that you have a vector, a non-empty space as that's given by the set of vectors v1, v2, v3 up to vn. So this is just a non-space set of vectors. So then the vector equation, here we can form a vector equation that is a linear combination of something, like the same way we did here. We can just form an equation for the linear combination of these vectors. So if you're doing that, you can have something like this. You can have k as being the element of all real numbers, or any real number, not all. So here you can have k1. You see that this we can define those things as a k1, k2, k3. So you can define k1 multiplied by v1, which is a vector, plus these are vectors here inside in a non-empty space S. All right. So and you can define k2 multiplied by v2 plus blah 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 plus kn multiplied by vn as being equal to 0. This is a standard definition of the linear independence and linear dependence. So here we're trying to find the solution of this, of which numbers can we put here, coefficients actually, that we can put here in order to get 0. Example for this one, if you are saying that we want 0 here, that means you are supposed to put 0 here, and you're supposed to put 0 here in order to get 0 here. All right, so let's do for this one also. So this already has a one solution. So if I want to get 0, since I said k can be any real number, I can say just k1 is equal to k2 is equal to k3 is equal to kn up to kn. All of these be 0. So when you multiply a vector by a scalar 0, you will get 0, right? So if we put zeros here in this space, already will get 0. So that's one solution. That's obvious. We already have that. So we call that a solution a trivial solution. So we are going to call that solution, and it's important to define linear dependence and linear independence. So we call that solution a trivial solution. Trivial solution. So that means that's a one solution that we already have. If we add all of these vectors and we put k here as k0, we have already one solution, which is as what we call a trivial solution. So and then let's define the linear dependent and linear independent. Let's define that. I want a space. Okay, I will write here linear dependent and linear independent. So the question is, when are you going to say that this system of vectors are linear independent or this system of vectors are linear dependent? So now we're going to define that. So you are going to define it like this. Remember, we said that k1 k2 plus it's v1 plus k2 v2 plus kn vn must be 0. So we already have a one solution, which is k1 0, k2 0, and also kn is 0, and we call this a trivial solution. So it's actually finding the value of k. So we found the value of k. We found that, okay, if k1 k2 up until kn is 0, we already have 0. So another thing that you can try to find, it's where, like, if k1 is not equal to k2 and this is not equal to even kn, but still this makes this equation to be 0. So we're going to call that a non-trivial solution. This is going to be a non-trivial solution. Okay, so now let's define the linear dependent and linear independent. Okay, so if the only solution to the system of vectors is a trivial solution, the only solution to the system of vectors, if you are given a system of vectors and you add all of them, and the only solution that you have for those vectors is a trivial solution, then you say that those vectors are linear independent. So that means this tells you that the system of vectors are linear independent, independent. But if you remember that any is a trivial solution, but if you find that you have an alternative solution, which is a non-trivial solution, therefore you say that those combination, the system of vectors are linear dependent. Those vectors are linear dependent. So if you have more than one solution, which one is going to be a trivial solution, and we have another solution, we say that the system of vectors are linear dependent. Okay, so we're going to do an actual examples actually to show these things. Okay, so go back and check those examples. One. All right, so and before we can just define rank. So rank is just going to be to the total number of vectors that are linear independent. So here it's just going to be the total number of vectors that are linear independent. and we're going to see that in this example. So here we have this first example. It says determine if the following sets of vectors are linear independent or linear dependent, and hence find the